Welcome to Chapter 14 on Lean Operations. This is the last chapter in the textbook we will cover this semester. There are two parts to this chapter, just as there has been on the others, so make sure that you see both of them. These are the learning objectives for this chapter. Once again, you may want to pause the video to read through the learning objectives and then come back and start again. So lean operations. This slide shows a definition of lean operations. It's a flexible system of operations that use considerably less resources than traditional systems. So I think the word lean is very descriptive. If you think of a lean cut of beef or chicken or some meat, you will imagine a cut of beef that has an absence or very minimum fat associated with it, and it's lean. So there's a lot of things that we're trying to do with lean systems. They tend to be more productive systems. If we're more productive, our costs should be less, and things happen quicker. That's the big thing we're trying to do with lean. If we're able to really do this, the time it takes to produce a product, the time it takes to do something should be considerably less, as much as half less in many cases. And of course, our quality should be improved as a result of this. Now, what's our ultimate goal? Our goal, of course, is to match supplies against demands. Any type of a operation system is going to be trying to do that. But we're trying to achieve a balanced system. And the slide shows in that second bullet kind of a definition of what a balanced system is. It's a smooth flow of material, a rapid flow of material, where things arrive just as when they are needed. Very smooth, but very rapid. But when I say rapid, I'm not talking about a frantic pace. It means things move fairly quickly, but no one seems to be working at a frantic pace in order for this to happen. So there's a YouTube video that we're going to be seeing next, and the URL for this YouTube video is shown here. And I've selected this YouTube video because I think it does a very good job of kind of representing in a kind of a humorous way what a good lean system looks like. So it's a Visa commercial is what it actually is. You may remember it when it was running on TV several years ago. But if you'll take a look, when you look at this YouTube video, try to see that there is a smooth flow, there's a rapid flow, there's a high productivity, there's a very short cycle time in this particular video.
The Visa check card. Because money shouldn't slow you down. Life takes faster money. Life takes Visa.
Now that we've seen the video, we have an idea of what a lean system kind of looks like and feels like. We didn't see anyone working at a frantic pace in there, but we did see something kind of humorous at the end, and that is the individual who was going to be paying by cash as opposed to credit card, where everyone else was paying by credit card. And that individual, by paying by cash, represented a disruption in the system. And it is paramount in order to achieve this balanced flow that any disruptions in the system are absolutely minimized. So this diagram here, I kind of like the look of it. It looks a little bit like a house in a way. We see the little symbol up at the top has a roof-looking top. So that's our ultimate goal, what we're trying to achieve with a lean system. So the ultimate goal is a balanced but a rapid flow. And we also have some supporting goals. That's kind of the frame of the house. We need to eliminate disruptions. We're going to have to do that very well in order to get this balanced rapid flow. We want to make the system flexible, and of course, we want to eliminate waste. And then sitting on top of everything is the foundation block. So any type of a structure or building needs to have a foundation, especially if it's a tall building. The foundation of the building needs to go down to bedrock. So the foundations that need to be set before we can really get these benefits are shown here. And those are product design, process design, personnel and organizational elements, and manufacturing planning and control. And later in the lecture, especially in the B part, we'll see that manufacturing planning and control is just abbreviated with the three-letter acronym MPC. So our supporting goals in Lean, again, is to eliminate disruptions. And the definition of a disruption is anything that could cause this smooth, rapid flow to be violated. It could be a material shortage. It could be some type of equipment breakdown. It could be a vendor who delivers poor quality material to us. Also, to make our system flexible, to be able to change quickly if the demand changes. So if we see our customers have taking a dislike to some product that we've been producing and a like to another one, and so the demand needs to switch from one to the other. Another way of saying that is our product mix is going to change. We need to be able to do that. And finally, to eliminate waste, especially any excess inventory. So, what is the definition of waste? The definition of waste is anything that is over and above the absolute minimum necessary. So, these are some examples of waste that could be present in a lean system, beginning with inventory. Now, for some of you accounting majors in the class that we've studied financial accounting, you know that inventory is shown in the accounting balance sheet as an asset. An asset is supposed to be something good. But in this particular instance, inventory is represented as a waste. A waste is something bad. So how could inventory be considered by accounting to be an asset and also be a waste as well? And the answer, it could be both. Overproducing. So one of the things that could cause us to overproduce, produce more than what we need to, there could be several things. One is an excessive amount of safety stock. Another would be a lot size policy that we are using that is going to cause us to produce more than what we need. One of the biggest sources of waste in an operations management system is just waiting time, just waiting for something to take place before it is your turn to process. And in some manufacturing environments, the total amount of time, the total cycle time, upwards of 80 to 90% of that cycle time is just waiting time, just waiting their time to be processed. So you might want to think about the next time that you're waiting in line to see an advisor on the second floor. If you feel like that the time that you're sitting in those chairs on the second floor is a waste, and I'm sure that you will agree with me that it is. Another wasteful activity is unnecessary transporting. So any material movement that is of a significant distance from one machine work center to another machine work center is a waste. Certainly the value of the material that is being moved from one place to another does not increase in value just by the process of moving it from one place to another. In fact, there's a possibility that the value of that material could decrease if, for example, it was dropped or it was lost or something happened to it in a way that damaged it. And whenever we move things, there's always a possibility that something like that could happen. So processing waste, okay? So scrap is another example. Our work methods that we use, if our work methods are not the most efficient. And then finally, product defects. If we have quality problems that cause materials that have to be reworked or even scrapped, also represents waste as well. And of course, there's other wastes we could think about besides these, but these are some pretty important ones. So let's take a look at the building blocks that our whole lean system sits upon. And as we saw in a previous slide, they are product design, process design, personnel organizational elements, and then finally manufacturing planning and control. So we'll start with product design. So once again, the engineers that design the product, if their design is not such that lends itself well to lean manufacturing and to quality, it's very difficult, if not impossible, to achieve that if the design does not lend itself to that. So what are some of the things that the engineering folks could do along these lines? One is to use standard parts. What's the definition of a standard part? A standard part is a common part that we have used for a long time. We have experience with this part. We know that it's reliable. We have a reliable supplier who delivers this. So if we have a need for a similar part as this in a new product, if at all possible, use a part that we have experience with. Now, engineers that I've worked with in my career, they love to design and they love to use new things. And, sometimes if the product that we're designing just absolutely requires us to use something new that we've never used before, well, then we have to do that. But if in any way possible, we could minimize the number of totally new parts that go into the product, we'll try to do that. Create a modular design where parts are interchangeable back and forth with each other. So modern computers today have a modular design. An example of a computer part that is modular is a hard disk drive. All hard disk drives, regardless of the manufacturer, are the same physical size, and they will fit into a standard motherboard. So you can interchange one hard disk drive with another hard disk drive. So if your hard disk drive failed, you can remove it and you can put in a new one. It's modular, it just fits right in. Or if you just wanted to increase the capacity of your hard disk drive, you could do that as well. So another thing is concurrent engineering. Concurrent engineering is a concept where while the engineering staff is designing the product and creating their engineering drawings, concurrently to that, the operations staff is also reviewing those drawings, and they are identifying the sources of supply. They are identifying any particular reliability issues or any producibility issues that may be difficult to produce in a cost-effective way. So the idea is that the operations folks are looking over the shoulder of the engineers, and if the engineers are making some decisions that are not necessarily going to lend themselves to efficient operations, the operations folks can whisper in their ears and say, why don't we do it this way? Think about this. This would make it a lot easier, and we can make this part for a lot less money. So concurrent engineering is an important concept today. Now let's talk about the building block for process design. So we're talking about the operations process now. So we'll talk about a number of techniques in the process design as shown on this list here, beginning with small lot sizes. So to refresh your memory of what a lot size is a inventory management policy that I have, which determines the quantity of the product that I'm going to either build or buy. In the lean philosophy, the ideal lot size is 1. I need one, I make one. I need another one, I make another one. Now, this ideal lot size of 1 is one of these theoretical things that you can't really achieve that. It's virtually impossible to have an ideal lot size of 1, but still, in a perfect world, that would be the ideal lot size. But we can reduce the lot size, and we will get a lot of benefits by doing that. Some of the benefits that will be achieved in reducing lot sizes are lower work in progress inventory, which means our carrying costs are low. There's also some benefits if for some reason we may have any quality issues. So if we have some things that didn't quite work out so well, and we've already completed some of these units in the lot, then there are fewer that have to be inspected to see if they're good or to be reworked, and that reduces the amount of time there. Toward the bottom of the slide, there's a couple of important points there, especially in increasing the visibility of problems. So if you're looking for something and you're in an environment where everything is absolutely cluttered, you might think of your bedroom, for example, if you have clothes all over the floor, all over the furniture and everything, and you're looking for something, just that clutter just makes it difficult to see things. It's a lot easier to see things whenever there's less material around. So if we have a smaller lot size, if we have any particular problems, they are easier to detect from just a pure visual point of view. In addition to reduce lot sizes, we need to reduce setup time. So let's define what setup time is. Setup time is the time that is required to prepare a piece of equipment to perform some type of work. So during the setup time, I'm not able to actually do any work. It's just the time it takes just to get ready to do the work. So an simple example of setup time that you can relate to as a college student is when your instructors are getting ready to teach a lecture, they have to either connect their laptop computers to the podium or to boot up the computer within the podium, to bring up any files, any displays, to start the overhead projector, all of that time that it takes just to get ready to begin the lecture is setup time. So now that we know what setup time is, if we're going to be reducing our lot sizes, building in smaller quantities, and have greater flexibility, which means that we're going to be changing our product mixes, that means we're going to have more frequent setups, switching the set time it takes to switch from one product to another product, and the time it takes to change over from making that product to another product. So we're going to have to get that setup time down to as small as possible. Now, in some cases, setup times, especially in some industries such as the steel industry or even in the paper industry, the setup time can be quite large. It can be measured in hours, 3 to 4 hours to set up a piece of equipment. Well, in a lean environment, that is just unacceptable for us. We're going to have to figure out a way of getting that setup time to just a matter of minutes. So one of the techniques of methodologies for doing setup reduction, going through and reviewing all the steps in the setup, changeover, and eliminating the ones that we don't need to have, is called single minute exchange of die, or SMED. In addition to reducing setup times, another thing we can do from a process perspective is to implement manufacturing cells. So one of the wastes that can occur is transportation time, just the physical movement of material from one machine to the other. A manufacturing cell is an organization of different pieces of equipment that is usually in a U-shaped or horseshoe-shaped configuration, as shown in the diagram on this slide. So each of the little boxes in this slide represent a different piece of equipment. So I have a product that is going to begin at machine 1, and when it finishes there, is going to machine 2, then machine 3, and so forth, until finally it finishes out through machine 10 and the product is complete. Now, the distance between machine 1 and machine 2 is very small, just a matter of a foot, or maybe even less than that. So manufacturing cells is a very important element in going lean, in reducing the travel distances. This also gives us a better utilization of our equipment, that is, it's being used more. And another thing is we're able to have fewer employees. So we could have an employee that maybe is doing the operations on machine 1, 2, and 3, and a different employee that's doing the operations on machine 4, 5, and 6. And if for some reason an employee is unable to come to work, we can cross-train those employees to where they can operate different machines, which makes us more productive. In addition to manufacturing cells and also to setup time reduction, we need to make sure that our quality is at its absolute highest. So one of the techniques in our lean toolkit is called JAKOTA. JAKOTA is a Japanese word, and what it basically means is the automatic detection of defects during production. The automatic detection of defects during production. Now, JAKOTA is a fairly difficult thing to do. Thinking back over my career, I can only think of one time in my career as a operations management person where I can say we truly had achieved a JAKOTA effect. What it was, I was involved with a improvement of a manufacturing process where we were building wiring harnesses. A wiring harness is a collection of wires that is used to interconnect different components in a electronic system. And wiring harnesses can be quite large. They could have anywhere upwards of 400 individual wires within a wiring harness. And if you have 400 wires in a wiring harness, that means that you have 800 wire ends in that harness. Each wire has 2 ends. And that means that you have 800 opportunities for making a mistake in connecting that wire in to wherever it goes. So our process before our Dakota was to assemble the wiring harness and then to send it to a machine that did an automatic detection of did an electrical test to see if everything was connected correctly. And always there were mistakes. There were miswires. So we had to then send it back. We had to make those corrections, go back to the electrical equipment, do another electrical test. Yes, we fixed some, but maybe there's some new ones that we now have, or maybe a few that didn't quite get fixed. Go back again for another rework, go back to the electrical test until finally we had proven that all the wire connections were correct. Well, instead we came up with a process where we had a microprocessor, basically a computer, that was able to detect each individual wire as the assembly operator was making that connection to see if the connection point was correct. And if the connection point was correct, then a green light emitting diode would turn on, indicating to the operator that that was correct. But if the operator had made a mistake, a red light emitting diode would turn on, indicating that a mistake had been made. And the operator could then repair the mistake themselves, and whenever the green light came on, they could go to the next wire. So what we found after we had implemented this new process improvement was we would complete a wiring harness and then go to the electrical test, and everything was fine. And we'd do another one, and everything was fine. Well, it didn't take us very long to realize, well, you know what? We don't need the electrical test anymore, because this Dakota was essentially doing the testing in the process of the production, and so we could eliminate the time for the test and further reduce the cycle time. Work flexibility. So one of the things we're trying to do, one of our supporting goals in Lean, is to being more flexible, okay? And these are some guidelines of being more flexible. So the definition of being flexible is that we're able to change our product mix. We're able to move as our customers change their particular needs and wants more rapidly. And some companies that have been less flexible in this area are no longer with us. So here's a list of some things that we could do. We've already talked about some of them. Take a look at number 5, use offline buffers. I was talking about some inventories, maybe some little extra inventories that we keep. Now, again, we don't want to do too much of this because inventory is a potential waste. We want to have a balanced system is another supporting goal we're trying to have. And one of the ways that we do that is with the concept of takt time. Now, it's spelled T-A-K-T, but it is pronounced just as if the K were a C, T-A-C-T, takt time. And takt time is it's a German word. It comes from a German word which basically means a rhythm or a balance. So some of you may have at some time in your life taken piano lessons. And if you've ever taken piano lessons, or if you've seen someone taking piano lessons, you'll notice that the piano teacher has a little instrument that is set on the top of the piano that moves back and forth, back and forth, back and forth. That's called a metronome. And what the metronome is doing is help each particular music score has a pace to it. It has a beat to it. And that the metronome is helping the student play the piano to the pace of the music. Well, in manufacturing, we want to have a beat. We want to have a pace. We want to have a rhythm. So when you saw the YouTube video you observed that there was a pace to that particular delicatessen. There was a rhythm to it. So there's an optimum pace. So tack time is something that could actually be calculated. We can calculate what that pace should be. And if we're able to achieve that pace, we can achieve this nice balanced flow. Inventory storage. So inventory may be viewed from an accounting perspective as an asset, and it is an asset. But if we have too much inventory, then it can be also a waste. So from the point of view of lean, if we have an excess amount of inventory, it's viewed as a waste. The little diagram in the bottom of the slide kind of paints an interesting story, an interesting concept of excess inventory and the problems that it caused. So if you take a look at the little figure in the left-hand corner, it's marked figure A. We can see that we have a little rowboat with some rowers on the water, and we have some big boulders of blocks at the bottom of the little lake that they're rowing down. And those rocks represent inventory. And they also represent the problems, the production problems that can, and the waste that the excess inventory causes. But by keeping this excess inventory, so the water level is essentially the inventory. The water level is the inventory, and the rocks are the problems, the production problems. So by keeping excess inventory, we're not able to really see what the production problems are. If you take a look at the next slide in the middle, we've lowered the level of the lake. We've lowered the inventory level. So by lowering the inventory level, it causes the real operational problems to become more evident and become more visible. And if they're more visible, then hopefully we have a chance to correcting those. So we can eliminate those problems or eliminate those boulders. So we see that in the slide to the left, we've eliminated the problems. The boulders are gone. You know, the inventory level is still, you know, pretty much the same as it was. So we're able to cruise along and with a lower inventory level. Poka-yoke. This is another concept. In this example, this is a Japanese word, poka-yoke. Basically means fail-safing. So when we, in our process of assembly, let's build into the process the elimination of even making a mistake. So we have to have the design has got to support this, but if we can do things in such a way to where there's only one way that things can be assembled, it cannot be assembled any other way than this, then that reduces the possibility of someone even making a mistake in manufacturing. Now we'll move on to the building block of personnel and organization. And to me, this is one of the most difficult parts of going lean because it really requires management makes some very different changes in the way that they look at things, especially their employees. And so we'll take a look at some of the elements of personnel and organizational differences, starting with workers as an asset. So you, my students, are the future business leaders of tomorrow. And most of you will, at some time in your career, be promoted to levels of supervision and management. Some of you will even be promoted to levels of senior management level and maybe even executive management level. I hope that when you get to those levels, that you understand that most employees are motivated, they want to do a good job, but we need to make sure that they have received the training in order to do a good job. And we also need to listen to our employees. Most employees know where the problems are. They come to work every day. They deal with the problems every single day. And they have ideas on what could be potential solutions to those problems. So we need to give them an opportunity to express themselves and to let us know what the problems are and what they think the solutions are. Cross-training our employees. So making them more capable, giving them the opportunity to be able to do more than one thing. It not only gives us greater flexibility from an operations point of view, but it puts more variety into the employee's life, so they're not doing necessarily the same thing every day. Coming to work is not necessarily potentially as boring as it could be, because today they may be doing something different than what they did yesterday. This concludes part A of this lecture. Welcome to part 2 of chapter 14 on lean operations. So we concluded the first part talking about the personnel changes necessary for a lean operation. We'll continue with that thread in the second part here. So another element of our personnel organizational is continuous improvement. So by now that you know that continuous improvement is the second of Professor DeLuke's 3 fundamentals. So we've talked about that quite a bit. So we need to continuously improve, and especially we need to continuously improve those processes that bring the value that our customers consider to be so important. So we need to build within our employees this attitude of continuous improvement. And I have to reflect back on my very first employer, Texas Instruments, and how lucky that I was to become an employee of that company, because the company had, from the day that I had initially joined, already a corporate culture of continuous improvement. And in fact, every employee, regardless of your position, was expected to make at least one improvement in the way that they do their job every year. So if you could not make at least one improvement in how you did your job, that was sending a message to management that maybe you weren't thinking about it as hard as you should have been. So we want to have a good positive pressure on our employees for continuous improvement. We want to encourage them, and we certainly want to recognize them for their ideas that they come up with. So public recognition of continuous improvement is very important to do. Another thing that we could do is change some of the ways that we collect our overhead costs using an accounting technique called activity-based counting. So activity-based counting, if we are measuring our labor in certain ways, activity-based counting kind of gives us a different perspective on that. So some of you accounting majors, I'm sure, will encounter this concept at some time in your accounting courses. Also, leadership and project management. So going back to my earlier comments about my students being the future business leaders of tomorrow. Leadership involves setting the direction, and leadership involves facilitating. And in many cases, leadership involves being the cheerleader. Leaders are not necessarily expected to always come up with the correct solution. So give your employees an opportunity to develop leadership. Give them an opportunity to learn project management. Now we'll move to our last building block in our 3 building blocks, and this is manufacturing process and control. And that's shown here on the title slide as just MPC. And there's a number of elements on it, and we'll take them one at a time. So the first one is level loading. The definition of level loading is we are producing about the same amount every day. Now this is extremely important in going lean. It's very important that our production output or our production volume does not have a great deal of changes to it. Because what are we trying to achieve? We're trying to achieve a smooth, rapid, balanced flow. If we are trying to produce 1 week 1,000 units of a certain part and the next week 10,000 units of that same part, that's going to be very difficult to achieve some type of a smooth, balanced flow whenever the volume changes so much. So we have to come up with the ability of building about the same amount every day. And notice I'm saying about the same. I'm not saying exactly the same. And there are some techniques for achieving this that's documented in your textbook, referred to as sequence cycles in our products mix, is determining the optimum number of sequence cycles. In addition to a level loading, we would like, where possible, to achieve a pull flow. So an MRP system uses a push flow. In a push flow, we are assembling from the lowest levels of the bill of material and moving upward in the bill of material. So you always have to start with something at the basic level and build up. So we are essentially pushing from one level to another. Now, push flow has its advantages. It also has its disadvantages. One of the disadvantages of a push system is that it gives us the possibility of having excess inventory, especially when we push material to a higher level, but there is some other missing component and we're not able to move that, to actually use that material that we pushed there until the other component arrived. So it is essentially sitting there and we have the wasteful aspect of excess inventory. A pull system is when we pull output from the preceding workstation only when it's needed. So we are pulling from the top of the bill of material downward to the bill of material. And the big advantage of a pull system is that it eliminates this unnecessary, wasteful inventory being sitting there waiting to be used. So we only pull inventory whenever we need them. Now, the pull system, in my opinion, and in many others' opinion, in our implementation of lean operations, is the last thing that we do. The last thing that we do. Because the pull system can be viewed as like a house of cards. If you ever take a deck of cards and you start to kind of build a little pyramid or something with them, they're very unstable, and all it takes is the slight movement of one card and everything will come crashing down. Well, a pull system is like that. Everything has to be set up. The disruptions have to be minimized before we can go to this. So it's the last thing that you do. Communication. So as part of our pull system, communications is going to go backward. When I say backward, I'm talking about going to preceding workstations. And also as part of a pull system, flow arrives just in time. So the YouTube video that we saw earlier, we saw things arriving just in time, just as a customer in the delicatessen was ready for their sandwich or their drink or whatever, it flowed into their hands. Visual systems. So the pull system is usually, but not always, a visual system. And the thing that allows us to determine when we need to do something, that gives us a signal or a authorization to produce something, is called a Kanban system. The word Kanban is a Japanese word that translates into English into the word signal or visual record. So a Kanban is a card, a physical card. Think of a 3x5 index card, or maybe an index card a little bit bigger than that, that has some information on it, the part number, the quantity. And that particular card is associated with a container that is going to contain this particular material on this particular part. So the Kanban system is our authorization to produce or to order from a supplier. We could have different types of Kanbans. We could have a production Kanban card, as well as a delivery card for moving material from one workstation to another workstation. You could also have a third type of Kanban card that I have seen in my experience for ordering from a supplier. Now, one of the things that we need to be able to do is to calculate how many of these Kanban cards that we need to have. So a Kanban card and a container in which we're going to keep the materials, we'll kind of think of those as essentially the same thing. So we have a little mathematical formula for calculating this, and it's shown on this slide. So the letter N represents the number of containers or the number of Kanban cards. There's one card per container. The letter D represents what the planned usage rate is for that material at that work center. So we consume about so many of these units on some unit of measure per hour, per day, whatever. The letter T represents the average time it takes us to get a resupply of that part whenever we run out. So we have a supply of those parts in a container, and we're going to be using them to do some type of operation. Well, before long, we're going to run out. Well, how long does it take us to get another container that has a full supply of those parts? So T represents what that time is. X is a variable that represents essentially safety stock, is what it actually is. Your textbook refers to it as a variable set by management for possible inefficiencies. Well, isn't that what safety stock is all about? To protect you against certain uncertainties. So that's what X is. X is usually represented as a percentage, like 20% or 30% or 10% or something like that. And then finally, we have the variable C. C represents the capacity, okay? So how many parts are going to be able to be put into this particular container? So every container, it has a fixed size, and we have for each part only one size container, and we have a certain quantity that can be held in that container. So here's an example of calculating how many Kanban cards that you need. I put an example in here, and if you see an example in here, you're going to see this show up on an exam, and you will have to calculate this on an exam. So in this example here, for this particular material, we are going to be consuming 50 units per hour. That is the usage rate. The time to replenish is 90 minutes. So it takes us 90 minutes after we have used all the parts in this container to get us a new supply in. And our safety stock variable is 20%. In other words, we want to have 20% more Kanban cards than what we actually need. And the number of parts that will fit within this container is 25 parts. So plug in those variables into the formula. So N is equal to dt times 1 plus x, and then divide all of that by C. So D is 50 per hour. Now, in this case, the replenishment time and the demand need to be in the same unit of measure. So 50 per hour, we have to convert the replenishment time to hours. Okay, so 90 minutes is 1.5 hours, so we've got that into the same unit of time measure. So in our formula, we'll use the number 1.5 for that. Our safety stock is 20%, so that's 0.2. And we do the calculation, and that calculates to 3.6 containers. Now, you always have to round up if you get any type of a fraction at all, and you most always will get a fraction. So, because you can't have a fraction of a container. You have to have an integer number of containers. So the correct answer in this example is that we need to have 4 containers. We need to limit our work in progress. Okay, so work in progress means extra inventory. So again, the work in progress is going to be determined most likely by our safety stock and also by our lot size policy. So if we reduce our lot sizes, by very nature, it's going to reduce our work in progress. Typically, we need to have a closer relationship with our vendors or our suppliers in a lean environment. So, first of all, we're going to have fewer suppliers and vendors. We may even only have one supplier or vendor. And however many we have, they're going to be few in number, and they're going to be the ones that we can really count on. Because in a lean system, especially in a pull system, you just cannot afford to have a part shortage. You cannot afford to have a part shortage. So again, going back to the YouTube video, there at the end, whenever the customer paid by cash, that represented a part shortage. That represented a disruption. And we saw the effect that it had on the entire lean supply chain. So we have to have vendors that deliver on time. In fact, we may want to give, in many cases, these vendors additional privileges to actually come into our plant and bring the materials out on our production floor. That's done quite often, especially in the automotive industry. Okay, and also we might also want to implement vendor managed inventory, which we'll talk about here in just a minute. Okay, many times lean processing systems reduce transaction processing. Transaction processing is what occurs with our ERP systems. So because things quite often are visual, this puts a less reliance on information systems. But please let us remember that these enterprise systems, we still need to do the accounting functions. So everything needs to eventually flow to the balance sheet and the income statement. So yes, we can reduce some transaction processing, but we cannot eliminate the transaction processing that's going to post the inventory, the accounting information that eventually flows to the balance sheet and the income statement. We need to keep our house in order. We need to do preventive maintenance. The definition of preventive maintenance is maintaining the equipment and, in fact, replacing parts that tend to fail before they actually fail. Before they actually fail. So, for example, if we have a machine that has a fan belt on it, so the fan belt turns, and eventually that fan belt is going to fail. Eventually it's going to fail. So we need to do periodic inspection of that fan belt, and when we see it starting to wear and start to have cracks in it that are indicators that it may fail in the future, don't wait until it breaks and then the machine can't be used. Go ahead and change it before it actually breaks. We need to do housekeeping. In fact, one of the very first things that we typically do in the implementation of Lean is something called 5S. Your textbook doesn't talk about 5S, but usually that's the very first step. And implementing 5S alone will have a tremendous number of benefits in reducing waste. So 5S is 5 different words that begin with the letter S. So the first word is sort. So if I have a lot of things I'm not sure whether they're good or bad, I have to somehow sort them out. And I sort them into 3 groups. One is a group that I don't need this anymore. I haven't used it in a long time. Throw it away. That's one group. Another group is, this is something I need, I use every day, I want to keep it. And the third group is, I'm not sure if I want to keep it or whether I throw it away. So we need to think about the third group. The group that is throw away, immediately throw it away. Set in order. In other words, a place for everything and everything in its place. Designate where each item goes. This is its place. It always goes right here. Shine. If it is in need of some type of repair or it needs to be cleaned or whatever, put it in good working order. Standardize. Let's make sure we do this all over the factory. And then sustain. If we ever see clutter starting to build up again, then we're getting away from 5S. Go through this again. Sort, set in order, shine, standardize. So a place for everything and everything in its place. And typically, that's the first step in our journey to going lean. Now, I put into the lecture kind of a comparison between traditional and lean. We'll talk about this. So from an inventory perspective, kind of a traditional system may want to have late deliveries where the lean is trying to go absolutely minimum. Deliveries from our suppliers. In a traditional system, we want to order in large quantities and have as few deliveries as possible. Where in lean, we want just the opposite. We want small quantities and we want many deliveries. From a lot size perspective, traditional, we typically have larger lot sizes, maybe even economic order quantity, which is larger, where lean is small. Setups, many setups in lean, where in traditional we have fewer setups. Suppliers, in lean, we have fewer suppliers and we have a closer relationship with them. And from employees, we view our employees as assets. We give them responsibilities. We listen to them. And in a traditional environment, employees are not viewed in the greatest light. So transitioning to a lean system. Here's a list of some things that could possibly get in the way. If you certainly don't have the commitment from top management. You're going to have a very difficult time doing this. Implementing lean works best whenever we choose those types of parts and so those types of products that are easier to work with. And we'll talk about some of those things. Sometimes it's easier to start small and lean. Pick a product line that you feel like lends itself to going lean and start with that. And if you achieve some good results, then you can start to incorporate the same results with those other products. Be prepared that there are going to be some difficult days. Going lean is extremely difficult to do. There's going to be a lot of pushback, usually from the employees. That's one of the reasons why we have to change our attitude in working with them. If we listen to them and we give them an opportunity to tell us where the problems are, their resistance to going lean will be reduced. So if management is not fully committed, if we don't have the cooperation of our employees, if we don't have our suppliers on board, these are things that could make this path to lean very difficult. Lean can also be implemented in the services industry as well. There are some things that we have to do differently whenever we do it, but essentially we're trying to do the same thing. We're trying to eliminate disruptions. We're trying to eliminate any waste. You may be interested to know that here at the University of Texas at Dallas, that a few years ago, our university president has designated that our campus and our processes will become lean processes. So he realizes the benefits of going lean here at the university, of reducing waste. If we reduce waste, we reduced cost, we reduced expense. If we reduce those, then we can keep our tuition rates down, which will be beneficial to our students. Just-in-time 2. JIT2 is a concept where we take this relationship with our suppliers and we kind of take it to the next level. The next level would be that we ask our suppliers to manage our own inventories. We are essentially outsourcing that responsibility of inventory management to our suppliers. Of course, before we do this, there's a great deal of trust that has to be built up. There's a great deal of information sharing that has to take place. So if we're going to be managing someone else's suppliers, we need to know what their inventory levels are today. We need to know what the demands will be for those particular products that we're going to be managing the inventory for, which means we have to give this information to our suppliers if we're going to ask them to manage our inventories. So VMI is a trend that has been taking place in operations management for some time, and it is a trend that will continue to take place. So from an operations strategy point of view, going lean is probably one of the most important areas that we could do. It works best in certain types of industries, certain types of products, and we'll take a look at where it works best in. So let's end this chapter by discussing the differences between lean and MRP, which we reviewed in a previous chapter. So from a production process perspective, lean works best where we have higher volume, where MRP works best where we have lower volumes. From a demand perspective, lean works best where we have a steady level loading type of demand, where we produce about the same amount every day, as we said earlier. MRP works best if your demand is lumpy. That is, it varies all over the place. The benefits of both systems are the same. Both MRP and lean have as one of their benefits to reduce inventory. They just go about it in a different way. From a scheduling perspective, both systems are trying to, again, do the same thing. MRP and lean are trying to schedule things just when they are needed. Not any earlier, not any later, but just when they're needed. So, from benefits and scheduling point of view, MRP and lean have a common goals, and they're trying to do the same thing, but they go about it in different ways. So their planning systems, lean quite often uses visual systems. A Kanban pull system is typically visual, where MRP requires a very sophisticated computer software. Lean uses a pull system, a Kanban system. MRP uses a push system. And lean works best where we have a shallow bill of material. What do I mean by a shallow bill of material? What I mean is we do not have a great deal of parts. So maybe something less than 20 parts within the product. There's a lot of products that have less than 20 parts. MRP works best where we have deep bills of material. So some of the products that I used to do material planning for, we had as many as 3,000 parts on the product, very deep bill of material. A lean type environment would never work where we have 3,000 parts. Remember, we can't afford to have a disruption. You can't afford to have a part shortage. If you have 3,000 parts, you're going to have part shortages. There's just no way of getting around that. So this concludes the second part of this chapter. This concludes the last chapter in the course. So I hope that you have learned some things about operations management and supply chain management, some things that will help you in your career.